Hi, welcome back. I realized when I did the last video, or after I did the last video, that I had left out one important part of this this final section 3 that we're going to be going over, or that we are in the middle of right now, and that is the idea of Kepler's third law of orbit. We've actually been using this equation in the past day or so in class, but I wanted to show you where it comes from. This relates two things. T, or our period, you can think of T as time, or the amount of time in seconds that it takes for an object to orbit a larger object, and A. Okay, now this is an acceleration A. This is the semi-major axis A. And to illustrate this better, let me just draw an ellipse right here. Well, let me start by drawing actually a circle. Okay, there's our circle, fairly circular, and in our circles we have an important measurement, that's our radius r. Well, in an ellipse it's a little different. I'm going to make an exaggerated ellipse right here. Hey, that's not half bad. Okay, and you may recall that in an ellipse there are two important points called foci, or each one is called a focus. And the distance, let's say right here is where the central gravitational body is, like the sun, for example. You probably remember that from the center of the sun to the closest point of approach of the orbiting body, we call that the perihelion radius, or perigee, or para anything radius. And from the center of the sun all the way to the furthest point of approach, we call it the aphelion or apogee radius. Oops, I don't want to do that. RA. Okay? But neither of these is really the true radius, because this is the closest radius, that's the furthest radius, and with an ellipse it's constantly varying. So what we use to measure what we call you could think of as the average radius, is what we call the semi-major axis. Well, the major axis is this distance right here. It's the long axis. Major axis. Okay, well, semi-major axis is simply half of that. Semi means part. So from there to there is what we call the semi-major axis, and we call that A. Now again, don't get this confused with acceleration A, because it's a different A, and eventually we have so many things in physics that you start running out of letters, so you have to reuse them, but that's what we're going to use for our semi-major axis. This distance from here all the way, from the very center of the ellipse all the way to the long edge, can be thought of as the average radius. Semi-major axis A is equal to average radius. So we can use the same equations for an ellipse as we do for an object moving in a circular orbit, simply by putting in the semi-major axis A where we would normally put in R. So that's what A is over here, our semi-major axis. So Kepler's third law of orbit develops a relationship between orbital period, time, and the distance an object is, on average, from the body that it's orbiting. It's a linear relationship. We say this is a constant right here because, well, there is a constant, and this constant is 4 pi squared over capital G times m. Now this m here this isn't the mass of the moon. I know we put capital M in our calculators as the mass of the moon, but this is really the mass of the body being orbited. So if this were the sun right here, for example, we would put in the mass of the sun there. Or if we're talking about an object going around the Earth, we would put mass of the Earth in right there. Okay, so this big M is the big body, the big planet, the big object that we are going around. But what this means is that for any object going around that body, the time it takes to go around it squared in seconds, divided by the semi-major axis, or you can think of it as the average radius, cubed, is going to be equal to this constant. The mass of this body, the central body, is not going to change. G doesn't change, 4 pi squared doesn't change, so that's a constant right there. And we call this Kepler's third law. In the next slide, I'm going to show you how we derive that, and then we can just go ahead and start using it. So we have, let's just say we have a circle. Okay, it applies to circles and also applies to ellipses as well. But we have an acceleration being directed towards the center. So we have a centripetal acceleration, and that's what's keeping this body in orbit around the larger body right here. Well, that centripetal acceleration is really caused by what? Is there a string attached to it? No, it's because of gravity. So the centripetal acceleration is the gravity that object is experiencing at that distance from the central body. And you know what, from now on, I'm just going to say sun. Let's just pretend we're going around the sun so it's easier. I'll just say this planet going around the sun. The centripetal acceleration that it experiences is equal to the gravity that it experiences at that distance from the sun. So let's write down what we know about centripetal acceleration. Well, we know centripetal acceleration from the last chapter is 4 pi squared times the radius divided by the period, or time in seconds, squared. And we know from this chapter that the gravity, now I'm not talking the surface gravity of the sun, I'm talking the gravity that the body is experiencing this distance out from the sun, is going to be capital G times the mass of the sun divided by radius squared. This equation right here we have been using the past few days. Well, since the gravity that it's experiencing is a centripetal acceleration, we can set those two equal to each other. And now we can develop a relationship between time to go around the sun and distance from it. Now again, remember, this r can be thought of as a, or the semi-major axis in an ellipse. So let's just simply rearrange this and put it in terms of t and r. So what I'm going to do is I'm going to put t and r on one side and all the constant stuff on the other side. So I'm going to bring t up, I'm going to bring g and m down, and we're going to bring this r down right there. So it's going to look kind of like this. 4 pi squared divided by, remember, gm comes down, g times the mass of, in this case, the sun, equals, t squared comes up, and this r comes down and joins the r squared, so it's going to be r cubed. Well, that's the same thing as saying t squared over semi-major axis cubed, and that's exactly what we have in this last slide right here. This is Newton, or I keep wanting to say Newton, Kepler's third law of orbit. That's how we get that. And so, since this is a constant, that is, for a given central body like the sun, the mass of the sun isn't going to change, g isn't going to change, 4 pi squared doesn't change, then this means for any body orbiting the sun, the time it takes to go around the sun in seconds squared divided by its semi-major axis or radius cubed is always going to be the same thing. It's always going to equal 4 pi squared over gm, which is a constant. So that means for any planet going around the sun, the period of Mercury squared divided by the semi-major axis of Mercury cubed is going to equal, remember, Mercury is our first planet, the period of Venus squared divided by the semi-major axis of Venus cubed equals period of Earth squared divided by the semi-major axis of Earth cubed, and so forth. You get the idea. So for any planets going around the same body, we can say that the period squared divided by the semi-major axis or average radius cubed is always going to be the same thing, and these are all equal to each other. So we'll do some problems in class that deal with that, and I hope that makes more sense now. Again, I think I introduced this in class a little before I actually had you guys watch the video, but that's Kepler's third law, and that's where it comes from. See you in class.